Section 8.2 is about graphs of polar equations. So we're going to use our understanding of polar coordinates, r theta, to sketch graphs of polar equations. And the equations look like r equals some function of theta. First, let's recall graphs of rectangular equations. So if we have some equation y equals f of x, the graph of that equation is, this is what we're defining. The graph of the rectangular equation y equals f of x is all pairs x, y that satisfy the equation. So for example, let's say f of x equals x squared minus 2x plus 3. So our graph, to graph this, we're going to think about all of the outputs of our function as y values. So let's see, the point 1 comma, let's see, I guess 1 squared minus 2 times 1 plus 3, which is 1 comma 2, is on the graph of y equals f of x, since 2 equals f of 1. And that's true of every single point on this graph. And then to figure out what the graph looks like, we plot all of those points, or plot some of those points, and then kind of connect the dots to get a rough idea. And if you have a graphing calculator or Desmos, they plot a lot more of those points and give you a much better representation of what the graph looks like. So we're going to do the same thing, but we're going to use polar equations instead. So the graph of the polar equation r equals f of theta consists of all points r theta that satisfy, and maybe these are polar points r theta that satisfy the equation. And then the collection of all those points gives us the graph. So let's do a few introductory examples, and then we'll look at some more challenging examples. So example, let's find several points on the graph of r equals 2. Then plot the points and sketch the graph. So here, right, we're thinking of f of theta, our function, is the constant function 2. So let's make a table. And this is probably what you did when you first learned about XY graphs. So here's theta, and here's r, which is really f of theta. So let's pick some like nice angles, theta, that we know, like negative pi over 2 is pretty nice, negative pi over 4, 0, let's do pi over 4, and pi over 2. Now, so since the function is constant, though, all of our r values are going to be the same. All of our r values are going to be the same. Now, just like in a table for a function of y and x, each of these is going to correspond to a point. Right? Usually we don't do this third column, but this corresponds to the point 2 comma negative pi over 2, the polar point. And this is 2 comma negative pi over 4. This is 2 comma 0, 2 comma pi over 4, and 2 comma pi over 2. Okay, now, right, we can plot these points. Here's our polar coordinate system. Let's label this outer radius 2. Okay, maybe that radius there is 1. Okay, and then let's start plotting our points. So 2 negative pi over 2. Remember, there's a few ways to get this. And we also want to think about, remember, negative pi over 2, we can also think of as straight down. So the point 2 negative pi over 2 is right there. And maybe let's use different colors so you can make this connection. Here's the point 2 negative pi over 4. Here, let's do 2 negative pi over 4. And this is the point 2 negative pi over 2. And then, okay, 2, 0. So the radius is 2, so that means we're all the way out here. The angle is 0, so that's actually going to land us right here. 2, 0, which matches up with the Cartesian coordinate as well. Just that's a coincidence. And then let's try 2 pi over 4. That's going to be right here. 2 comma pi over 4. And then the last one, we'll go red again. 2 pi over 2 is right here. And now we can see, hopefully, maybe, right, that all of our points are going to have an R value of 2, and then the angles can be whatever. So now in black, I'm just going to connect the dots, and this is actually, maybe we can see, this is just the equation for a circle of radius 2. These are all of the points that have an R value of 2. Okay, let's do another example. Let's sketch a graph of theta equals pi over 3. Now this one's a little bit different. This is kind of like what we're going through is like y equals some constant and x equals some constant. So if you remember from Cartesian coordinates, these just give you straight lines, and they're some of the most basic types of Cartesian coordinate equations that we have. Y is a constant, x is a constant. So the first two we're going through is r is a constant and theta is a constant. Now our table is going to be a little wonky here, just like if you think about what the tables for y equals a constant and x equals a constant, those are also kind of wonky. But we can do the same thing where we do theta and then r, so we can get our theta values and our r values, and then that will give us our corresponding point. Okay, but all of our theta values actually are pi over 3, because the theta value is fixed. Pi over 3, pi over 3. So all of the theta values are always the same. And then we just pick a few r values that we think might be useful. So let's do -2, -1, 0, 1, and 2. And that these corresponding points are -2 pi over 3, -1 pi over 3, 0 pi over 3, 1 pi over 3, and 2 pi over 3. Okay, now let's start plotting these points. Remember, there's two ways to plot them. First, we can find r and then the angle, or vice versa. Let's do, right, the angle is pi over 3. So the angle is pi over 3 means that all of our points have to be on this red dashed line. So all of our points have the same angle of pi over 3. This dashed line corresponds to all of the points that are on that have that corresponding angle. So then the negative 2 pi over 3 is, right, this direction up here. This is positive r values. And down here, these are negative r values. So negative 2 over 3, sorry, negative 2 pi over 3 is going to be right there. Negative 1 pi over 3, sure, let's say that it's right there. Maybe this isn't perfectly to scale. So that's our negative 1 pi over 3. And this is how, if we're not sure about the scaling here, by labeling the points, that's the way to communicate very clearly what we're talking about. 0 pi over 3, r of 0. All right, now this doesn't happen when we're talking about x by r definitions. We can't have an r value of 0. It always has to be positive. But in the case of our Cartesian coordinate system, our polar coordinate system, right, if the r value is 0, it doesn't matter what the angle is. You're always going to be at the origin or the pole. Remember, we call the origin the pole in the polar coordinate system. 1 pi over 3, let's match that other 1. I think it's going to be out here. Positive 1 pi over 3. And then the 2 pi over 3 is going to be right there. And then, of course, right, we missed a bunch of r values, but they're all the r values that are in between. So now if we just connect the dots, we can see that the equation theta equals pi over 3 is going to correspond to this solid line at the angle pi over 3. Goes forever in both directions. Right, lots of examples. We're going to do another example. This one's going to be a little bit more complicated. Let's sketch the graph of r equals 2 sine of theta. R equals 2 sine of theta. Okay, so let's make a data table. Theta r is 2 sine of theta, right? This is our f of theta. Our function of theta is 2 sine of theta. And then we'll also get the corresponding points here, just to keep everything organized. Let's use theta values of 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Alright, so we need to know the sine of all of these angles. Okay, so sine of 0 is 0, so this is going to be this is going to be 2 times 0, which is 0. This is going to be 2 times sine of pi over 6. Sine of pi over 6, if you think about, right, our 30, 60, 90, here's pi over 6, pi over 3. Okay, this y value is 1, the x value is positive root 3, and the r value is 2. I guess I'm thinking of this as in the first quadrant. So this is going to be 2 times sine of pi over 6 is 1/2, so this is just going to be 1. It's going to be 2 times sine of pi over 4. Sine of pi over 4, let's do another. Right, there's pi over 4. This is 1 square root of 2. Sine of pi over 4 is 1 over root 2. So this is going to be 2 over root 2. Sine of pi over 3. So this is going to be 2 times sine of pi over 3. Sine of pi over 3 is root 3 over 2, so this is just going to be square root of 3. 2 times sine of pi over 2. Sine of pi over 2 is 1, so this is 2. 2 times sine of 2 pi over 3. Right? If we use, I'm running out of room, so I'm going to just write the answers here. So 2 times sine of 2 pi over 3 is the same as sine of pi over 3. Okay, because of symmetry. All right? So sine of pi over 3 is root 3 over 2. So this is just root 3. Sine of 3 pi over 4 is the same as sine of pi over 4. 1 over root 2. So we get 2 over root 2. Sine of 5 pi over 6 is the same as sine of pi over 6. So we get 2 times 1/2, which is just 1. And then sine of pi is 0, so we get 2 times 0 equals 0. Right? So the symmetry of the sine function between the first and the second quadrants allows us to see, right, there's symmetry in our answers here. So here we have the point 0, 0. Here we have the point 1 pi over 6. Here we have 2 over root 2, comma, pi over 4. Root 3 pi over 3. 2 pi over 2. Root 3, 2 pi over 3, 2 over root 2, comma, 3 pi over 4, 1, comma, 5 pi over 6, and 0, comma, pi. I'm going to erase this stuff over here, over here, and I'm going to bring in a polar graph so we can see what these things turn out to be. All right. So let's start by plotting 0, 0. That's right at the origin. And then let's make the radius of this, let's label the radius here. Let's say that that radius out here is 2, because that's the biggest radius that we have. I kind of want to fill up as much of this as we can. And then let's call this, let's call this line right here, let's call that 1. So our first point is 1 pi over 6. So that's going to be right there. Let's color coordinate this. That's the point 1 pi over 6. And then we have the point 2 root 2 pi over 4. So 2 root 2, what is that? So let's use green. So 2 over root 2 simplifies to just square root of 2, which is about 1.4. So pi over 4, 1.4 is going to be right about there, because I'm going to imagine that this is 1.5. So the 1.4 is just underneath that, just before that 1.5. Okay, square root of 3. All right, square root of 3 is about, that's like 1.7, it's like 1.73, 1.75, something like that. So we go to pi over 3, 1.7, that's about right there, halfway between the 1.5 and the 2. And then we're going to start over with the 2 pi over 2, so we go straight up. And then, because of the symmetry, right, symmetry allows us to, I'm going to go kind of backwards, right, so 2 pi over 3, so those two yellow dots kind of correspond to each other. The two green dots should correspond to each other, so that was like right about there. The two blue dots are going to correspond to each other, so that's going to be right there. And then 0 pi, we actually come all the way back around. 0 pi is right there. And now, to figure out what this graph looks like, we just kind of connect the dots, and we get something like this. And if you go to Desmos actually does have Cartesian graphing. You can switch the grid from rectangular to Cartesian, Desmos has polar graphing, you can switch the grid from rectangular or Cartesian into polar, and this is actually a circle of radius 2. So this equation, r equals 2 sine theta, gives us a circle of radius 2. And if you, I guess maybe we should say, when you go farther, right, so if we do another row, right, we'll just do one more row. The next angle we would do would be 7 pi over 6. So we would get 2 times, and then we'd actually get negative 1/2, because sine is negative when we're in the third quadrant. So it's going to be negative 1. And that's going to actually map, so it's going to be, the point is going to be negative 1, 7 pi over 6. That is actually the same, right? That is exactly the same as 1, is the same as 1 pi over 6. So this point and that point are the same point, right? They both land right here. And that, as we keep on going down here, if we keep on going, adding more and more rows, we're just going to keep repeating this original set of points over and over and over and over. So there isn't like a second circle, there isn't anything else going on. We just end up repeating that same shape over and over and over. All right, let's do another example. So let's sketch the graph of r equals theta. Okay, so the radius equals the angle. So let's make a data table and see what we can come up with. Theta and r are always going to be the same. So I think the challenge here is to figure out what our angles are. So, figure out what our angles come to as like a decimal. So let's start with, there's a little bit more to this question. For 0 less than theta less than or equal to 3 pi. So we don't want the whole graph, we only want the graph for some particular angles. So let's start out with 0, and then r is 0, so our point is 0, 0. So we start out at the origin, and then let's do pi over 4. So then our r value is pi over 4. So I just want to think of pi over 4 as a decimal. We don't do that very often, but for this case it will be very useful. And it's about, it's 0.79. 0.79. Okay, and then let's maybe do pi over 6. Nope. Pi over 3. It's also pi over 3. Let's do pi over 2. Pi over 2. Nope, I forgot to make those points. Pi over 3 is about 1.05. 1.05. Pi over 2 is about 1.6. 1.6. Let's start skipping a little bit. Pi, let's call it 3.14. 3.14. And then let's do 3 pi over 2. 3 pi over 2. So that's 3 pi over 2. So that's going to be like, let's just do 4.7. 4.7. Let's do 2 pi. 2 pi, that's 6.28, so 6.3, 6.3. Let's see, what's next? 5 pi over 2. And then finally 3 pi. It's about 7.8. 7.8, and 9.4, 9.4. These are, obviously, these are approximations. All right, now let's graph and see if we can see what happens. All right, let's make this outer radius, let's see, 2, 4, 6, 8. Yeah, let's make this outer radius 10. So then this is 2, 4, 6, and 8. So those inner radiuses are 2, 4, 6, 8. So we start at 0, 0. And then we're at 0.79, 0.79. So this is, so at pi over 4, we're like less than 1. So we're on the pi over 4 line and we're less than 1. So like right there. And then we're at pi over 3 and we're just over 1. So not much farther really. It's like right there. Pi over 2, we're at 1.6. So when we're, right again, right? Pi over 2, I'm looking straight up. And then 1.6, I guess we're a little farther out. Something like that. Then we'll start rotating through our colors again. 3, so at pi, we're past, we're like just past 3, so out to there. 3 pi over 2, we're at 4.7. So 3 pi over 2, we're past 4, but not quite to 5, something like that. 6, so at 2 pi, we're at 6.3, so we're maybe right out there. At 5 pi over 2, so 5 pi over 2 and pi over 2 are coterminal. 5 pi over 2 and pi over 2 are coterminal, so this is also, that's 5 pi over 2. And then pi is the same as 3 pi, or sorry, not the same as, coterminal with 3 pi. So at 5 pi over 2, again, we're straight up, but we're at 7.8, so that's almost out to the 8 line. And then at 3 pi, we're at 9.4, so we're almost all the way out, something like that. Now, let's try to connect these dots, and what this is going to look like, again, this is terrible because I'm drawing it by hand, but if you go to Desmos and graph it, it will be much better. And it should look like a spiral that's getting bigger and bigger and bigger. A spiral that keeps on getting bigger and bigger and bigger. There we are. That's my rough sketch of this graph from 0 to 3 pi. And we're going to do one more example, just lots of examples. I think that's the best way to understand this. And then you can also, right, you can use Desmos and make up as many practice problems as you want. So let's sketch the graph of r equals cosine of theta. So let's make a data table and figure out what we got. So our function is cosine of theta. That gives us our radius. We get these corresponding points. Let's use our, the kind of easy angles that we can figure out the cosine of relatively easily. 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. And let's start doing some computation. Cosine of 0 is 1. Cosine of pi over 6 is, what's that, square root of 3. Cosine of pi over 4 is 1 over root 2, which is, which is 1 over root 2. Sorry. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. Cosine of 2 pi over 3 is partnered with cosine of pi over 3, but instead of positive 1/2, it's going to be negative 1/2. Cosine of 3 pi over 4, again, I'm thinking of the XYR definition, and 3 pi over 4 and pi over 4 are very similar, except the x-coordinate is negative. So we get negative 1 over root 2. Cosine of 5 pi over 6 pairs up with cosine of pi over 6, but it's negative instead. And then cosine of pi, cosine of pi is negative 1. So we have the points, let's see, 1, 0, root 3 pi over 6, 1 over root 2 comma pi over 4, 1/2 pi over 3, 0 pi over 2, negative 1/2, 2 pi over 3, negative 1 over root 2, 3 pi over 4, negative root 3, 5 pi over 6, and negative 1 pi. And I just realized that I got these two wrong. Should be let's see, root 3. No, cosine of pi over 6 is root 3 over 2. Root 3 over 2, and cosine of 5 pi over 6 is negative root 3 over 2. Okay, is that it for mistakes? I think that's it. I'm going to label this point 2, point 4, point 6, point 8, and 1 for our radiuses. And then we start out with r is 1 and the angle is 0. And then r is root 3 over 2. Root 3 over 2 is, so root 3 over 2 is approximately 0.87. So at pi over 6, we're at 0.87, so pretty far out there. Yeah, pretty far out there. What about pi over 4? 1 over root 2 is about 0.7. So at pi over 4, we're at, what about there? Pi over 3, we're at 1/2. Pi over 3, we're at 1/2. Well, right there. Pi over 2, start rotating through, we're at 0. So the distance 0 means we're going right through that point. 2 pi over 3, negative 1/2. So angle 2 pi over 3, and then negative 1/2, so we have to go backwards down to here. So 2 pi over 3, negative 1/2. And actually, yeah, okay, sorry, I don't want to spoil it. 3 pi over 4, that corresponds to 7 pi over 4, so we're at negative 0.7. Right there. Negative root 3 over 2, 5 pi over 6. 5 pi over 6 corresponds to 11 pi over 6. Actually, I want to change up these colors. right? Just to show you that this negative 1/2 corresponds to, so those two yellow ones correspond to each other. They're mirror images of each other. And then the 3 pi over 4 and the negative 0.7, those two green ones correspond to each other. And then the negative root 3 over 2, 5 pi over 6. So 5 pi over 6, right, again, corresponds to 11 pi over 6. Since it's negative, we're going backwards, so the blue one above and this blue one correspond to each other. And then the pi negative 1 is actually exactly the same as this one. This is 1, 0, and also negative 1 pi. And now, if we keep on going, we're actually going to keep on repeating this pattern over and over again. So now if we connect the dots, again, it's hard to see with my crappy picture, but if you plot this in Desmos, you're going to get a circle that's supposed to be a circle of radius 1/2. And that's it, just lots of examples for this video.